Welcome back to Grade Academy on chemistry, atomic structure, and this is lesson 3. Now, this image, this classic image that you have of the atom, we know about the nucleus and we know about the protons and the neutrons inside from the previous lessons. We're going to focus on the electrons now. And there's a few people. Big player has to be Bohr. But before Bohr gets a chance to do the working out of what these electrons are, we already know quite a bit from William Crookes, who was talking about the cathode rays. He saw the electrons in action and saw the paddle wheel move to the side. We've already done this. We know that they got named. It was decided to name them as electrons. And then J.J. Thomson discovered a number of things about them. Let's move myself out of the way there for a second. And he discovers them. He calls them electrons on advice from Johnston Stoney. And he has the plum pudding model, imagining them within that circle, that big sphere. And he knows that they are negatively charged, so he works out the charge to mass ratio. So that's all done. We've all of that done. The next thing that we have to understand is the charge on the electron. And this is discovered by an American called Robert Milliken. And he does it by what is known as the famous oil drop experiment, which is measuring the size of the charge of an electron. And he did this accurately. Now, this picture is a combination of an image I took from the internet and labels. It's much more clear in your notes, but this is as big as I can get it at the moment. But what he does is he takes some oil drops and he charges them. So these are charged droplets and they're sprayed into this upper chamber. Now gravity will allow some of the drops to fall down through this slit or gap. Your eyeball basically is looking in here with magnification at the drop as it begins to fall into space. This part of the screen is positively charged and this part is negative. So what this drop is doing, if it's filled with negative charge, it would fall down, it would be drawn up by the positive bar, the anode. It would fall and it would be repelled away from the negative cathode. So when you adjust this dial and give enough power, this will actually float because it's being repelled upwards and being attracted upwards as well. But if you can actually get exactly the amount of energy required to make this negative enough to repel this, then you can get a measure of the charge. Now, all you have to know was his name and what he did. He measured the charge on the electrons. He found it accurately, and his famous oil drop experiment. Now, you don't have to be able to draw that drawing. This is the guy and what he did. That's all you have to know. And so he basically said there's a charge and it was much smaller than any atom. And so therefore an atom had smaller particles, subatomic particles, which we've already been discussing. Now, move myself out again. So here we have the boy, Niels Bohr. Now he is absolutely probably one of the main players in the whole thing. He's like Ernest Rutherford. He has come up with a really, really important response. So we have electrons in fixed quantized energies, and he defines energy levels, and he's famous for his 2n² formula. Now, what was it? He demonstrated the existence of energy levels that electrons will occupy within an atom. Now, so I'm going to click on and take you to the next picture. Now, this is a little rainbow that I made, a little spectrum of color, and I laminated it. And as you can see red, orange, yellow, green, blue, indigo, and violet. And if you look at that, that's what we know as a continuous spectrum. Now you can see that with a big pen. You can actually see that with crystals. You can see rainbows. It's all the same thing. It's where white light has been divided into its visible colors, the ones that you can see with our eyes, which are designed to recognize color. Now, a new technique called spectroscopy was available where you could shine bright light of different sources in through a prism. It could get split up, and if there was nothing interfering with it, you got this continuous spectrum. But this next picture I would like you to see. This and this are closely related, as you can see. What you've got is a series of chunks dug out of this continuous spectrum. Now, this spectrum here is called an absorption spectrum. It's called that. And this one is called an emission spectrum. Now, you know that if it slid back in, it would take all the places up. So one is the other part. Now, this has two names. That one's an absorption spectrum, and this one is an emission, like emitting a sound, an emission spectrum. Now, as I said, they are all related, and this sort of sequence, I just took a scissors and I literally cut wherever I felt like it. But this, they found, was unique. Now, what Bohr could only do was to look at this, and he studied this and he studied these, but he did so with hydrogen. Now, the hydrogen, I'm going to click back now for a second. The hydrogen was in a fluorescent bulb, quite similar to what Crookes had used in his cathode ray tubes and what we have in fluorescent bulbs today. So the gas was in the chamber, and instead of getting one continuous line, he could see these lines, and they were unique to hydrogen. Now, what he does is he tries to visualize what's happening. Now, this was a simulation that was provided to all the schools and to all the chemistry teachers at the time when the new syllabus was being provided. So this is from the Department of Education. It's a little simulator. And this is representing that nucleus that Rutherford had found. And this represents the single little hydrogen atom, this little guy. And he's going around in a particular energy. Now, you also have to think about a spring. And a spring vibrates if you let it. And then it can vibrate faster. And that would mean that it's got more energy. Okay, so you've got to think about it doing that or doing that. So we want to think about it like that. But now Bohr imagined it a bit like the moon going around this Earth. It was in an orbit. And this is what he did. We know now that he's going to be corrected, but he's thinking of that. These are lines. This is like the first energy, where the electron is at the moment. This is like the second energy level, which he's famous for for discovering. Third, fourth, and fifth. They look like they're getting closer together. They are. But this is a big jump, an energy jump. Now, we never say light when we talk about light energy. And down here, hopefully you can see it. I'm going to move me about another little bit. Down here are the emission spectra, like we saw. Now, what he saw was, he said, imagine the little electron going round the nucleus, and it's in its current shell, its current state, its energy. It's got a certain amount. And so what he suggested was you gave it a small photon of energy, a little piece of energy. That could be heat energy. And when you do your flame test, that's what you're giving it, heat energy. And what happens is the electron absorbs that energy, takes it in, and moves to a higher energy level. Now, what you need to see is where this line is. So it's down here, and it's going to jump to there, because I'm going to go from the first energy level to the second energy level. And this is what happens. So let's give it a little bit of energy. And this energy causes that electron to jump to that energy level. And one of these lines wobble. Now, he couldn't see the line wobbling, but he could imagine it. So what he was looking at was this, an emission spectrum. But what he was actually visualizing now was an electron in a higher energy level. It took up that energy. And then what was going to happen is it was two things you have to say, excited and unstable, and it's going to fall back down. So it's going to go from the n equal to 2, he decided to call the energy levels n, and he would drop it to 1. So he's going to fall back down, and this time he's going to fall from there to there, or from here in. And let's see that. Now, This part is not really visible. Because it's the Lyman series, it's not visible to the naked eye. There's the Lyman, there's the Balmer, and there's the Paschen series. The others are not on your course, so I'm not going to deal with them. But these ones, the ones that fall down to the n equal to 1, are visible in the ultraviolet area of the spectrum. And they could see that, but we can't see it with our naked eyes. The ones we can see with the naked eye, like the one I made with the rainbow, they're part of the Balmer series, and they are falling down to the 2nd level. So this time I'm going to make it go to the 4th level. I'm going to make it excited and unstable. You can see the electron is now going way out here to the 4th level. This time it's excited and unstable and it's going to fall, but this time I don't want it to fall all the way down to the 1st level. I want to fall down from the 4th to the 2nd, so that would appear as a coloured light in the Balmer series. So I'm going to take it from the 4th down to the 2nd. The energy is being taken away from it now. As it falls from there to there, and this would be where that line was. They weren't random. They were very much fixed. Now I'm going to come out of that for a second. So he studied the emission spectra of hydrogen atoms that had been given energy, electrical energy, and he found a series of lines of specific fixed energy, indicating that only specific jumps or absorbance and emissions were possible in an atom. Now, line spectra, as opposed to a continuous spectrum, provided strong evidence for the existence of energy levels. That's energy levels. Let me move me. Of energy levels, okay, within an atom. Now, if I just go back one space, he sees this. Now, look here. Do you see where that gap is? That's exactly corresponding to that. What he said was the electrons absorbed that piece of energy in order to jump up to the excited unstable. And when they were falling back down, they released exactly the same amount of energy as they had taken in, which is why that and that are one of the same part, the one continuous spectrum. So they used them to jump up and left gaps. They are absorbed. That's a piece of absorbed energy. And these are the pieces of emitted as they're falling back down to the energy level. And this was really significant. So he's famous for that. Now, this is a picture again provided by the Department of Education. And in this one, I like it. You have the Lyman series of all of the high levels. This is the energy, the lowest available energy level. And the electrons are falling down and they make what is called the Lyman series. It's in the ultraviolet region and it's falling back to the n equal to 1 energy level. This is called the Balmer series and this is falling to the n equal to 2. And the Paschen series is falling down to the actual n equal to 3, which is in the infrared, which you can feel, but we can't see it with our eyes. Now, we have to know those 3. So how do my pupils learn it? Well, they do it this way. They know Paschen, passionate red, infrared, Paschen red, so the infrared. Balmer is visible, and Lyman is the ultraviolet light. Lie out, man, for a tan, Lyman. Okay, I don't care how you remember it, but that's how my pupils remember it. Okay, he is really, really important for his definition of an energy level. Now, different books have different definitions. The word fixed is quite straightforward. Why should you do anything different when it's straightforward? It's very simple English. Another word is quantized, quantity, and people get confused with that word. So fixed is fine. An energy level is the fixed amount of energy that an electron can occupy within an atom. He's not outside the atom. He's in these areas. Now, the levels start closest to the nucleus, and then Niels Bohr went a little further. He worked out a formula to work out the maximum number of electrons that would fit into each model. And I'm sitting in front of it, so I'm going to come back down here, and it's 2n squared. So in the first energy level, if you put 1 there, square it, 1 squared is 1, multiply by 2, the maximum is 2 electrons. If I put 2 there, 2 squared is 4 and 2 4s are 8, and then 3 3 squared is 9 and 2 nines are 18. And that would have been exactly like junior cert. And then when you put 4 in there, 4 squared is 16 and 2 16s is 32. Now you're leaving junior cert and you're getting into the realm of leaving cert higher. Okay, so Bohr has not only given his name to the energy level definition, the definition of an energy level, and used the word fixed level of energy, that who can occupy electrons within an atom. That definition is critical. It's absolutely critical that you actually know what that is. Now, so he does all of that. And when he does, he doesn't know about something else. He doesn't know about a whole lot of people walking behind him on what he knows and what he's learned, and they're going to fill in some extra gaps. Now, I want to go back to the picture that I made, of the photograph of the little model I made. And if you look here, if you're looking with microscopes as they were doing, that might have just appeared as one gap, and that might have just appeared as one yellow line. And there was a big gap here, a big gap there, a big gap there, and a big gap there. And he called each one of those energy levels, or transitions is what he called them. It took some time after his first theory, when he started producing all of that. A number of other people climbed literally on his knowledge, his shoulders of knowledge, and actually then built on what they found. And they found that this wasn't just one full colour. There was little sublines. And eventually, after Bohr had sort of not marched away, but people were adding to his information, so he said there are energy levels. Scientists then found that there were energy levels and they were subdivided. And they decided to call them sublevels. And they also had to get other scientists, Schrödinger and a number of others, to actually work out whereabouts they were. Were they actually sitting in a particular place? Now, I don't know where I put my spring, but sublevels. Now, you have to know what an energy level is. Think about that. You could pause the video and remember what it was. If you did, an energy level is a fixed level of energy that electrons occupy within an atom. So a sublevel is a group of atomic orbitals. Oh, I haven't mentioned the word orbital yet. All of which have the same energy. So sublevels have the same amount of energy, but now we're talking about something different. Now, found the spring. Okay, so you saw me doing this to represent the little electron whizzing around. Bohr is no longer getting it all right, because it's not like a little planetary. It's not a particle. It could be a bit more like a wave. Okay, so now more like a wave. And this wave is moving, right? And whereabouts it is, well, we don't know. So somebody had to do some maths and work out where exactly all these electrons were. Are they in a particular motion, like Bohr thought they were moving around in the circle like you saw a few minutes ago? So a number of people have come into this idea, and a man, he's German originally, but he spent a lot of his life in Dublin. And he Erwin Schrödinger worked out the regions in space for the probability of finding an electron. So if I know I'm doing this in front of my own face, but if I swung this spring around a little bit, whereabouts would you find it? Well, you can't exactly say where exactly it is at any one moment in time. Okay, let's just do it. That's catching the light a bit better. You don't know whereabouts it is, but you could put a boundary at where it would probably be. And this is what orbitals were. And they found that some electrons occupied a spherical orbital, just like the picture that we started this lesson off with, and the stylized image that it has. And then others worked out that some of them went in what we call a dumbbell structure. So I have to do this correctly, like that. You'll see it in a minute. And these others looked a bit like a dodie, which is not required on your course. So they were atomic orbitals. All of these energy levels have definite regions in space around the nucleus, and they're described as orbitals. So an orbital is a region in space where the probability of finding an electron is high, okay, really high. Now, I drew this picture. Now, I know this is actually a little picture trying to represent an electron in an area. Now, this is like a planet, and obviously this is a rocket going around. And we're not dealing with anything like that at all. I know that. But if you know that somewhere out in the atmosphere and beyond the atmosphere there may be satellites, you would be drawing a circle around the Earth, and that area would be where you'd find the satellites. So a roadway is a region in space where the probability of finding a car is high. A field is a region on the planet where the probability of finding a car is low. So basically, an orbital is a boundary, an area within which there's a likelihood of finding an electron. And that definition is really important. So I'm going to go back to it. Orbitals are regions in space where the probability of finding an electron is high. Okay. Now, so what do we have to know about orbitals? There are s orbitals, and they're spherical, and the maximum capacity of electrons you can put into them are 2. The dumbbells are called p orbitals, and again, you can only have 2. And in d orbitals, you're not required to know what they are, so I'm not going to move me about again. The number of electrons in each case is 2. Now, an s orbital is going to do that, okay? And a p orbital is going to do that, or that, or that, but they're dumbbell. The d orbitals are not required. And so there you have it. Bohr, Milliken, the energy levels, and the orbitals. Thank you for watching this Great Academy lecture, and until next time, happy learning.